Welcome everybody to the Selected Topics in Mathematics online edition for the 29th of May 2026. Today our talk is on the Codenominator and a modular involution of the real line, and our speaker is Muhammed Uludag from Galatasaray University.
Perfect.
Muhammed, you may speak.
Okay, thank you, Rebecca. The title is somewhat unusual because the codenominator is a strange word, but I hope that I'm going to be able to explain that the term is justified. So, while the abstract of the talk, I'm going to talk a lot about the Fibonacci numbers. We all know what it is. So it starts with 1. The next term is also 1. And the remaining terms are always the sum of the preceding two terms. So it goes like this. And the question is there some, can we extend this sequence to Q, to the set of positive rationals? It is defined on the set of positive integers. So is there something between F5 and F6, for example? What is the Qth Fibonacci number of a rational index? So the spoiler is that the Qth Fibonacci number is going to be an integer, and I'm going to denote this by FQ, and F is called the codenominator function. For example, the 23 over 31st Fibonacci number is going to be 107. So let's start with the denominator. But before doing that, well, let's see denominator function. So we all know what it is. It's a function from the set of positive rationals to the set of positive integers, sending P of Q to simply Q, where P and Q are relatively prime. And this function satisfies a system of functional equations. The denominator of x over 1 plus x is denominator of x plus denominator of 1 over x, and the denominator of 1 plus x equals denominator of x. And in fact, well, it also satisfies that the denominator of 1 is 1. And, well, let's check this. So here are the equations. Now we check the second. We start with the second equation. So the denominator of 1 plus x is denominator of p over q plus 1 if x is p over q. Well, we just sum it. It becomes denominator of q plus p over q. And if p and q are relatively prime, and these two numbers are also relatively prime, so the denominator of this number is q. So this is verified. As for the second equation, we also set x equals p over q and substitute. So we get p over q plus 1. And, well, multiplying both sides with q, we get p over p plus q. And this time we see that, well, since these two numbers are also relatively prime, the denominator is p plus q. Well, the q is already the denominator of x, and p is obviously the denominator of 1 over x. So we have checked both equations. And if we impose that the denominator of 1 is 1, these three equations, in fact, determines the function denominator on the set of positive rational numbers. And the numerator is simply denominator of 1 over x. Well, in fact, this system defines the function denominator recursively on the Calkin-Wilf tree. And as you remember, this is a tree which is generated by this rule, starting from 1. So we substitute 1 here, we obtain 1 over 2 here and 2 here, and we go on applying the same rule. We can produce all rationals, and by following this production, we can also produce all values of denominator of the denominator function. Well, we have a system of functional equations, and, well, we are mathematicians. What do? We play with such equations. So let's play. I'm going to substitute 1 over x on the left-hand side here. and 1 over x on the left-hand side here also. This gives the functional equation, a system of functional equations. F of 1 over 1 plus x equals f of x plus f of 1 over x. And f of 1 plus 1 over x equals f of x, if you substitute here. And we can show that this system is consistent. It has a unique solution if we fix f of 1 to be 1. And we are going to call this solution the codenominator and denote it as f, magenta f. And the codenominator function is going to be defined to be the codenominator of 1 over x. So let's compute some values. So this is my system of functional equations that I've shown for your convenience. So if we set x equals 1 in the first equation, what do we get? Here we get 2. And here x equals 1, but f of 1 was already 1. So we get that f of 2 equals 1. And here also, if you set x equals 1 here, this says f of 1/2 equals f of 1 plus f of 1. So f of 1/2 is 2. And we can go on. If we set x equals 2 by using these functional equations and using the previously found values, we can compute f3 over 2 to be 1 and f1 over 3 to be 3, and so on. This way we can produce all values of f. And in fact, this system defines the function f recursively on what is called the drip tree of rationals, which is generated by the rule. It is similar to the calculus tree, but the production rule is somewhat different. So the children of x are 1 over 1 plus x and 1 over 1 plus x. We can produce all positive rationals this way too. And here we can see the connection with the Fibonacci sequence. Let's try to compute f of x plus 2. Well, what do we do? By using the first equation here, and this is an equivalent form of the first equation, right? This is the very first, but if you substitute 1 over x in the first equation, we get that f of 1 plus x equals f of 1 over x. So if I set x equals x plus 1, here I get x plus 2 equals f of 1 over x plus 1. So here. But f of 1 over 1 plus x equals f of x plus f of 1 over x. And f of 1 over x, again from this equation, equals f of 1 plus x. So f of x plus 2 equals f of x plus f of 1 plus x. And this is the well-known Fibonacci recursion. And since f of 1 equals f of 2 equals 1, as we have just found, we see that f extends the Fibonacci sequence to the set of positive rationals. And the codenominator function, since the codenominator is f of 1 plus 1 over x, which equals f of 1 plus x, the codenominator is just the Fibonacci sequence shifted by 1. So we see that f extends the Fibonacci sequence to positive rational arguments. We can show that this is a surjective function, but it is not injective. And furthermore, for every rational x, the sequence f of x plus 2, f of x plus 2, etc., forms the generalized Fibonacci sequence, which is sometimes called the Fibonacci sequence, defined by the initial values g0 equals f of x, g1 equals f of x plus 1, and the remaining terms are defined by the Fibonacci recursion. So this is what is called the Fibonacci sequence. And in fact, any Fibonacci sequence can be obtained in this form. Well, let us see some further codenominator values. As we have just shown, f of n equals the nth Fibonacci numbers. F of 1 over n, this is the n plus 1 Fibonacci number. f of 1 plus 1 half, f of n plus 1 half equals the n plus 1th Fibonacci number plus f of fn minus 1th Fibonacci numbers, which is called the Lucas sequence, by the way. And we can compute some other values like this. And well, here we have a list of codenominator values of numbers of the form 41 over n, where 41 is a randomly chosen prime number. And as in an integer, for example, here we see that the first line here, the Fibonacci, the codenominator of 41 over 51 is 3 times 5 times 59. So, what are the properties of this codenominator function? The first property is what I call the Fibonacci invariance. We have this functional equation, which we can iterate. So according to this equation, f of x equals f of 1 plus 1 over x. But if I iterate this, I obtain that this equals this equals this, etc. And if I wrap this up expression, I get what is called the Fibonacci matrix. And the iteration tells us that the codenominator of this expression equals to codenominator of x. And from here, if you set x equals 1 here above, we get that the codenominator of fn plus 1 over fn is 1. And we can show that the codenominator of fn over fn plus 1 is n. And as I mentioned that f is in fact surjective, so f assumes every positive integral value infinitely often. Here's another property. As we have just shown, we have the Fibonacci recursion. But if we can iterate this. If we set x equals, if we set x plus 1 here, substitute in place of x here, we obtain that f of x plus 3 equals f of x plus 2 plus f of x plus 1. But I can use the value of f of x plus 2 given here. So f of x plus 3 equals 2 times f of x plus 1 plus fx. And I can iterate. And the iteration gives us the codenominator of x plus n equals the n Fibonacci number times the codenominator of x plus 1 plus the n minus first Fibonacci number times the codenominator of x. This is the Fibonacci recursion. So, as you all know, any rational number can be written uniquely as a finite continuous fraction, here like this. And we can, from the previous recursion formulas, we can compute the codenominator of this continuous fraction recursively. So we have this formula. This is just a rewriting of the previous recursion formula. And we have a generalization of the previous formula, which I call the splitting rule. So the Fibonacci, the codenominator of this continuous fraction can be split. And if we do split, then so this equals this first piece multiplied by the second piece, but this is not enough. We have to add this product as well. And we also have the symmetry rule. We can easily show that the codenominator of 1 minus x equals the codenominator of x. In fact, the denominator function also satisfies some of these properties. We also have the reversion, Euler's reversion formula for continuous fractions. So if we revert the continuous fraction, then the codenominator remains the same, just like the denominator function. We have the arithmetic periodicity in several senses, by the way. So the Fibonacci sequence is known to be periodic modulo m, where m is any integer. For example, if m is 2, the Fibonacci sequence modulo 2 is 0, 1, 1, 0, 1, 1, 0, 1, 1, etc. Here we have the Fibonacci sequence, and here we have the Fibonacci sequence modulo 2. So it is periodic, and its period is 3, which is called the Pisano period. Pisano is just another name for Fibonacci, by the way. So similarly, we have several periodicities. For example, if we fix all components here, but if we just move one of them, the jth component, it goes like 1, 2, 3, 4, 5, etc. And this sequence is periodic modulo m for any m. And in fact, we can show that the period is divisible by the Pisano period, the previous period. And in fact, this is true for semi-regular continuous fractions as well. And several similar periodicity formulas. For example, f of k times x modulo m is periodic for all k and all x. I mean, for all x as k moves, 1, 2, 3, etc. We have another property, divisibility property. Well, Fibonacci sequence is known to satisfy this property. So the mnth Fibonacci number is divisible by the mth Fibonacci number. And as a generalization of this, we have this. So if we multiply the partial quotients of a continuous fraction by m, all partial quotients simultaneously, then this codenominator value is divisible by f of m. And similarly, if we repeat the continuous fraction several times, so this, again this, again this, as many times as you wish, this is always divisible by the codenominator of this. And there's a version of these formulas for semi-regular continuous fractions as well. Well, we have the involutivity property of the codenominator. This appears to be complicated, but in fact, this says that a function, which I'm going to describe soon, which is called the Jimm function, is an involution. And this formula is shown by using that the denominator function can be expressed in terms of the codenominator function. So if we know the codenominator of x and the codenominator of 1 over x and the codenominator of this this expression, then we can find the denominator of x. Well, another property, we have the function which I call the codiscriminant. So it is defined as f of 1 over x squared minus f of x times f of 1 over x minus f of x squared. And this function is two periodic on the set of rationals. In fact, the codiscriminant of 1 plus x equals minus codiscriminant of x. And well, this is if x is in the interval 0, 1, we have the codiscriminant 1 minus x equals codiscriminant x also. Well, there are, as you know, billions of Fibonacci identities in the literature. And even now, I'm sure that somebody is discovering a Fibonacci identity somewhere and publishing it on the archive. And you can, one can generalize many of these Fibonacci identities to the codenominator function. And one idea to do about how to do is to replace fn in the formula by f of x. And sometimes you have minus 1 to the power n somewhere in the formula. And you replace that by the codiscriminant of x. For example, we have what is called the Taguras identity, which can be generalized like this. So this is if x, y, and z are all integral, then this is the Pythagoras identity, and here we have -1 to the power something. And in the generalization, well, three of these numbers, I mean, we have three numbers, but two of them must be integral. So if just one of them is rational, then this formula is still valid. And in fact, this formula is a generalization of the famous Okines identity and the Catalan identity. And well, if you want to have some fun after this lecture, you can take your favorite Fibonacci identity and try to generalize it to the codenominator. So, well, another instance where the Riemann zeta, where the codenominator appears, is the following formula. If we take the following sum, fq to the power s times f of 1 over q to the power s over the set of all positive integers, then this sum equals zeta s square over zeta 2s. Well, in fact, this is a very simple result. And the reason is that these pairs, f of q and f of 1 over q, in fact, gives an alternative enumeration of the set of all pairs of coprime positive integers. Okay. Now let's talk about the function Jimm. The function Jimm is defined to be the ratio of f of 1 over x divided by f of x. So this is a function defined on the set of positive rational numbers. And equivalently, since our first functional equation says that f of 1 over x equals f of x plus 1, the Jimm function can be defined this way as well. So the idea is that x equals the numerator of x divided by the denominator of x, and x is called a rational. And Gmx is the codenominator of x divided by the codenominator of x. So we can call this the co-rational number. And well, f is an integral function, so it doesn't make sense to plot it on the set of rationals. However, Jimm is a rational valued function, so we can try to plot it. And its plot looks like this. It is discontinuous, many jumps everywhere. So this is the plot on the interval 0, 1. We can plot it on the whole real line as well. You see two symmetries, symmetry with respect to this axis, and another symmetry with respect to this axis. This symmetry means that the function is is an involution, and this symmetry is a certain functional identity. So, well, these limit values are in fact here, the limiting value here is the golden ratio. Here also this, so it goes to infinity here, and this point is the golden ratio. And the two values here are the conjugate of the golden ratio. So in case you are one of those people who are obsessed with manifestations of the golden ratio in the nature, so this plot contains many golden ratios. In fact, any interesting feature that you can see here is related to a golden ratio. So what about the properties of this function? First of all, as I said, it is involutive, and it can be shown by using that involutivity identity of the codenominator function. It is equivariant with respect to the operator 1 over x. That is to say, Jimm of 1 over x equals 1 over Jimm of x. But although this appears complicated, it's a direct result of the definition here. So if Jimm is defined like this, then we always have this commutation identity or equivariance identity. So moreover, Jimm of 1 minus x equals 1 minus Jimm x. So this is also a kind of equivariance equation. And it says simply that the operators or functions 1 minus x and Jimm commute. We also have a twisted equivariance with respect to minus x. But in order to introduce it, we have to extend the function to the set of negative rational numbers as well. So we extend it like this so that this equation is satisfied. So extension and the equation are the same. And we have, using two of the previous equivariance relations, we can obtain that Jimm of 1 plus x equals 1 plus 1 over Jimm of x. So excuse me, can somebody say hello so that I know that I'm not talking to the void?
Hello.
Hello.
Hello, you're there. Okay, thank you.
Hi.
And so, in fact, Jimm is related to the Farey tree in the following way. So we all know how this Farey tree is produced, starting from the numbers 1 over 0, and here in this case 1 over 1. We apply the Farey sum rule, the wrong way to sum two rational numbers. So we get 1/2, and by applying this rule recursively, we obtain what's called the Farey tree. So Jimm, in fact, is related to an automorphism of this tree. And this automorphism does the following thing. For example, if we have a zigzag path here like this, I hope that it's visible. So the Jimm sends this zigzag path to a straight path like this. Okay. And vice versa. So if you have a straight path, or path segment like this, this automorphism of the tree sends this straight path to a zigzag path. So there's a way to, formalize this in the following way. So we start from this vertex, and we twist this tree on the plane 180 degrees, which gives us an automorphism of the tree. And now in the second step, I can do the same thing to the branches down to this root 1, 3. And we can do it here also. And I can continue downwards by twisting all vertices here. Well, this gives an automorphism of the tree, and we can plot these automorphisms. So the first twist gives me this, the second twist gives me this, the third twist this, etc., which converges to the plot that I've just shown you. And in fact, this sequence of automorphisms converges to an automorphism of the Farey tree, studied by Conder. And it is induced by Dyer's outer automorphism of the group PGL2Z. So how can we compute Jimm? If x is given in a continuous fraction form like this, let us denote 1 sub k, a sequence of k ones, like here. Then the Jimm of this continuous fraction is obtained by we replace n0 by a sequence of n0 minus 1 once, as here. And then I put 2 between, and in place of n1, I put n1 minus 2 once, so 1, 1, 1, 1, 1, etc. And I put 2 again, and then I put many ones also, and 2 minus 2 many ones, and 2, etc. Well, this won't always work. For example, sometimes when n2 is 1 or 2, so this is going to be 1 sub 0 or 1 sub minus 1, and I have to explain what to do in that case. And I have the following rules which tells us what to do. For example, if I apply those rules to discontinuous fraction, this gives me 1 3 sub 3 minus 1, 2 1 sub 3 minus 2, etc. And in the end, I have also 1 sub 3 minus 1. So the image of this is discontinuous fraction. If I do the same, apply the same rules to discontinuous fraction, well, I have this number. So we can extend this definition, this computation of Jimm values to, in fact, all irrational numbers using precisely the same rules. And for example, the value of Jimm at this irrational number becomes discontinuous fraction 1 1 2 1 2 1 2 1 2, etc. And similarly for discontinuous fraction. So we can extend this function to the set of all real numbers by taking limits. And if you do so, and if you concentrate on the rational values only, rational values of x, then these functional equations are satisfied everywhere. For every irrational value of x. So Jimm of 1 over x equals 1 over Jimm x. Jimm of 1 minus x equals 1 minus Jimm x, and Jimm of minus x equals minus 1 over Jimm x. Well, however, these three operators, 1 over x, 1 minus x, and minus x, they generate the whole projective general group over the integers. And these functional equations, in fact, they show that the Jimm acts as the automorphism of the group PGL2Z. Alternatively, we can say that Jimm is an equivariant function for the PGL2Z action on R. So to be more precise, for all irrational x and for every integral matrix, unimodular matrix, we have Jimm of mx equals alpha of m times Jimm of x. This is not the usual multiplication, of course. So alpha of m is a matrix, which is obtained, which is the image of m under Dyer's automorphism. And this automorphism is defined as above, sending 1 over x to 1 over x, 1 minus x to 1 minus x, and minus x to minus 1 over x. So it is defined on the generators of PGL2 like this, and one can verify that this is compatible with the group relations in PGL2Z, so it's a well-defined automorphism. Well, perhaps this is not very important, but in fact we can express Dyer's automorphism alpha in terms of the codenominator as well. And well, what is nice and very interesting for me here is that these equations show that Jimm is in fact a kind of equivariant modular function, which means that if x is a continuous fraction given like this, and y is given like this, and if x and y have identical tails, then Jimm of x and Jimm of y do have identical tails as well. By applying the rules about how to compute Jimm, this is readily seen. So this says that Jimm respects tails of continuous fractions. And this is just another way of saying that it sends PGL2Z orbits to PGL2Z orbits. So it induces an involution of the moduli space of pseudo lattices, which is defined to be this quotient, R divided by the PGL2Z action. Well, this is a terrible space, I know. It is not Hausdorff. But we can consider this as an analog of the modular curve in case where we replace this by the upper half plane and the action is much nicer. The quotient is called the modular curve. At least, I mean, slightly, we have to slightly modify this. We have to consider the PSL to Z action. So this Jimm acts on this analog of the modular curve, the real analog of the modular curve. So it's a kind of modular function, equivalent modular function, or equivalent modular form, I think. So what about the analytic properties of Jimm? Well, we can show that Jimm is discontinuous at rationals, but it is continuous at every irrational point. It is differentiable almost everywhere, and the derivative vanishes almost everywhere. Moreover, it is of unbounded variation on an interval, and it has jump discontinuity from Q. And in fact, we can compute the value of jump at every irrational point. How do we do it? The jump at this number is obtained by reversing the continuous fraction, computing the codiscriminates, and well, inserting here. So now I'm going to discuss what Jimm does to quadratic irrationals. As we've just seen, the value of Jimm at this periodic continuous fraction is also eventually. It is not absolutely periodic, but it is eventually periodic. 2, 1, 1, 1, 2, 1, 1, 1, 2, 1, 1, 1, etc. And it is easy to see that Jimm sends every eventually periodic continuous fraction to an eventually periodic continuous fraction. However, these eventually periodic continuous fractions are precisely the real quadratic irrationals. So Jimm sends real quadratic irrationals to real quadratic irrationals. Well, in fact, there is one exception to that. So if we denote the set of all real quadratic irrationals by K, Jimm defines an involution of this set. Well, here we see some examples. The effect of Jimm on quadratic surds, which shows that it is highly non-trivial. It is not something algebraic. Here we see the effect of Jimm on Markov irrationals. So here we have the famous Markov irrationals. They grow quite widely. They become more and more complicated. However, their Jimm values appear to be much simpler. So recall that Jimm restricts to an involution of the set of quadratic irrationals, which one may call the real multiplication locus. And it sends PGL2Z orbits to PGL2Z orbits. These two facts shows that, in fact, Jimm induces an involution of the set K divided by PGL2Z. This is, well, let us denote this by pi. This set pi is a subset of the moduli space R divided by PGL2Z that we have just discussed. And moreover, concerning the action of Jimm on quadratic irrationals, we have the theorem that Jimm commutes with the Galois action on this set. So Jimm of Xi bar equals Jimm C bar. Another way to say this is that if Jimm of A plus square root of B equals X plus square root of Y, then Jimm of A minus square root of B equals X minus square root of Y, where B is a non-square positive rational number. In fact, we can identify this set of set PGL2Z dividing K, the set pi, with the set of cycles or periods, N1, N2, etc. And Jimm, well, as we just seen, acts on this set by preserving the cycle length. I mean, by cycle length, I mean the sum of all these numbers. so it preserves the sum, but it doesn't preserve cycle length. The Galois action is simply the cycle reversal. And these two actions by Jimm and the Galois action, they commute. And they do have some common fixed points. For example, this cycle is a common fixed point for both the Galois action and the Jimm action. So now I will do a little trick. The equation Jimm of 1 over x equals 1 over Gmx can be expressed alternatively as follows. Well, just pick a number, set y equals 1 over x, then, well, xi equals 1. And because of the rule or the functional equation, Jimm of y equals Jimm of 1 over x equals 1 over Gmx, we get Jimm of x times Jimm of y equals 1 as well. So this equation, functional equation, can be written in this form as well. Xy equals 1 if and only Jimm of x times Jimm of y equals 1. Well, it looks like a very weak form of homomorphism with respect to multiplication. So now, if you do the same for the remaining functional equations, we get the following for reformulations. So the second functional equation says that x plus y equals 0 if and only if Jimm of x times Jimm of y equals minus 1. The commutation with 1 minus x says that x plus y equals 1 if and only if Jimm of x plus Jimm of y equals 1. And, well, we also have this reformulation of the fourth functional equation, which can be derived from the previous ones. Now, what am I going to do? I'm going to set y equals x bar, where x is a quadratic rational, so and y is its Galois conjugate. So these functional equations become x times x bar equals 1 if and only if Jimm of x times Jimm of x bar equals 1. And we have the remaining equations. But since we have the computation with the Galois action, we can rewrite this as, we can put the bar on Jimm of x out of the parenthesis, and this number x times x bar equals the norm of x in number theory, and x plus x bar is called the trace. So this equation becomes norm of x equals 1 if and only if norm of Jimm of equals 1. Trace of x equals 0 if and only if norm of Jimm of x is minus 1. Trace of x is 1 if and only if trace of Jimm of x is 1. And trace of x equals norm of x if and only if trace of x equals Gmx equals trace of norm of Gmx. Well, let us discuss the first equation. This says that norm of x equals 1 if and only if norm of Jimm of x equals 1. So it's Jimm restricts to an involution of the set of elements of norm plus 1 in quadratic number fields. As an example, so we have quadratic irration of norm 1. Its Jimm is this number, and you can check that it's also of norm 1. Concerning the function equation relating traces and norm, this says that trace of x is 0 if and only if norm of Jimm of x is minus 1. And from our list about quadratic surds, you can check that every number on the right-hand side is of norm minus 1, because the left-hand side is always trace 0. For example, here the trace of square root of 10 is 0, of course. And the norm, as you can check, is on the right-hand side is minus 1. And we have similar facts concerning norms and traces. Well, finally, let us talk about the transcendence. That is to say, how Jimm behaves on higher algebraic numbers. So by now, we know that if x is a real quadratic irrational, then Jimm x is a real quadratic irrational. And the question is, can we generalize this to all algebraic numbers? That is to say, if x is an algebraic number, then Jimm of x is also algebraic. For example, Jimm of cube root of 2, is it an algebraic number? So to answer this question, at least conjecturally, let us first take a look at the continuous fraction expansion of the cube root of 2. It looks like this. And in fact, it looks like a typical irrational number. If you take a typical irrational number, a transcendental or irrational number, its continuous fraction will look like this. We have some very big numbers and many ones, for example. Observe that there are many, many ones. Sometimes very big numbers, 534 here. And if I compute its Jimm, it looks quite atypical. We have many, many ones. For example, here I have 500 and something ones, because this number 534 will become 532 ones here. So starting from here till here, I have 532 ones. And we have the Gauss-Kuzmin theorem, which says that for almost all real number, the continued fraction partial quotients obeys the following statistics. If you take an arbitrary number from the interval 0, 1, the frequency of ones as partial quotients is 0.41. Frequency of twos is this. Frequency of threes is this, etc. This is a logarithmic rule. And if a number obeys these statistics, and if you compute its Jimm, then it's easy to show that the Jimm of x obeys the following statistics. The frequency of ones is just 1, as we have seen in the case of 2. So there are many, many ones, and in fact the frequency of ones here turned out to be 1, and the frequency of other numbers are naturally 0. So we have, this leads us to the transcendence conjecture, which says that if x is an algebraic number of degree higher than 2, then Jimm of x must be transcendental. Because if x is algebraic of degree higher than 2, then experimentally, as we have just seen, x obeys the Gauss-Kuzmin statistics. But this means that Jimm of x violates the Gauss-Kuzmin statistics in a very bad way, as we have just seen also. And because of the same experimental belief, Jimm of x cannot be algebraic, because people did many, many experiments, and it turns out that continuous fractions of algebraic numbers, except quadratic irrationals, obeys the Gauss-Kuzmin statistics. And we have a stronger version of this transcendence conjecture. I would like to finish with the connection with the quantization, because I think I don't have much time left. And well, this is quite a new result by Ovsienko and Mourier-Genoud. Well, a quantization of Q is a representation. Well, first we need a representation from PGL to Z to PGL to CQ, and together with a map from P1Q to P1CQ, which is an equivariant. That is to say, phi of mx equals phi of m times phi of x. So pair of functions, a representation and a map, satisfying the equivalence condition. And moreover, we require that the quantization of m, that is to say the phi of m, to be equal to Euler's quantization, that is to say 1 minus qm, divided by 1 over minus q. Just to compare invariance with equivariance, invariance means that phi of mx equals phi of x, and equivariance says that phi of mx equals phi of m times phi of x, or applied to phi of x. So Mourier-Genoud and Ovsienko discovered the representation which sends the operator 1 plus x to 1 plus qx, minus 1 over x to minus 1 over qx. And it can be extended to the whole of PGL to z. And we have the associated quantization, which sends the number 1 plus x to 1 plus q times x. Minus 1 over x quantized equals minus 1 over q times quantized x. And in fact, if x is written as a continuous fraction, as a negative continuous fraction like this, then we can explicitly write down the quantization of x in this way. And what can we do? We can plot these functions, quantization functions, or the functions phi. Where is phi? These functions phi. It is possible to plot them, which we did. First for positive values, so fix the value to be q, and you can plot the function phi of x. It looks like this. Not very bad, with some jumps, etc. So this is the monotonic regime, we can say. However, if we set q to a negative value, which we call the anti-monotonic regime, we get something weird, very strange functions with many, many jumps. And especially when q is minus 3, this plot looks suspiciously similar to the plot of the Jimm. In fact, this is how we discovered the next theorem. If you consider the Möbius transformation of f of x equals x plus phi over minus phi times x plus phi square, and its conjugate, then f of the quantization of x specialized to this value, where phi is the golden ratio, 1 plus square root of 5 over 2. So if you specialize this quantization to the specific value, and if you take its f, then we get the function Jimm. So if you are interested in these results, and if you do some further exploration, you may take a look at the recent paper of Curtis Macmillan from 2024, where he studies some lattices isomorphic to Z2 star free product Zm inside PSL2R. And these groups do have some automorphism groups, which will give rise to some functions similar to Jimm. And we have quite a classical paper by Marston Conder concerning group actions on the cubic 3. And there are, besides the automorphism extension of the modular group by the automorphism, there are 4 other groups which may be interesting from this point of view. Well, I think I have to stop here. I'm already beyond my time. Thank you for your interest. And Rebecca, if you're still there,
Yes, I'm still here.
I can take your questions.
Okay. So are there any questions from people who aren't me first?
I have a couple of questions. Firstly, you showed this list of Jimm applied to Markov irrationals. I was wondering if you can see or if there are any known patterns to those numbers.
Yes, there are some families. Just a minute, where is my... Okay, so you can still see my presentation, right?
Yes.
First of all, it is not a very exciting result because, you know, Markov numbers, they forget about the conjecture, right? Mm-hmm. So they don't distinguish between different appearances of the same number in some branch of the tree. So perhaps it's not very interesting from that point of view. And yeah, you do see some patterns. For example, well, Fibonacci numbers themselves are among the Markov numbers, right? Even index Fibonacci numbers, like we have, well, 13, 44, 34, 89, etc. You don't have 55, but you have 89, etc. And, well, obviously, the corresponding irrationals are this, and you can observe that there is some simple rule. So some quadratic sort minus something, and these numbers, in fact, all defined up to PGL2Z action, and you can get rid of these minus ones. So you can just consider square root of 6 to be a Markov irrational. And beyond this, I mean, there are some other families like this, but beyond this, I couldn't find an algebraic, kind of expression for all Markov irrationals.
Okay, thank you. And just quickly, this transcendence conjecture, is that known for any specific cases? Are there any examples of?
No.
Okay,
thank you.
thank you. May I ask, is there any study that's been done on the pre-image of the Jimm? So if you say which numbers could the Jimm of be to be a certain number or a certain type of number?
So it's an involution. So we can answer that question quite easily.
Are there any more questions?
I suppose I could ask one question to, if you could explain something a little bit more. When you talked about the Farey tree and what Jimm does to paths in the Farey tree, could you explain that a little bit more? Because these zigzag paths correspond to regular continued fractions, if I'm not mistaken.
Regular continued, how do you mean by regular continued fractions?
I mean, if you embed the Farey tree in, say, the upper half plane, and you look at any number on the line, real line, and you take a cutting, a geodesic between that number and infinity, and you look at the regular continued fraction for that number, it will create a pattern of going backwards and forwards, backwards, forwards, backwards, forwards.
Yes.
And I was wondering if
I mean,
if that's what you meant by that.
Okay, so of course, yes. So paths, well, where is my 3? I'm trying to find the 3. Of course, paths to infinity. Yeah. So here we have the, oops. Okay, here we have the Farey tree, right?
Mm-hmm.
If you start from 1/2 and go to infinity on this tree, this is precisely a regular continued fraction. It precisely corresponds to a regular continued fraction. So I have given you a formulation of Jimm in terms of continued fractions. So that rule precisely says that if I have a sequence of ones, 1, 1, 1, 1, etc., for example, 7 ones, it becomes, I mean, having ones means that you are making a zigzag in the continued fraction. And if you have a number, n, it means that you have turning n times in the same direction, like this, or like this, or like this. So the Jimm exchange those patterns, I mean straight paths with zigzag paths, and zigzag paths with straight paths, which means that it replaces a sequence of ones with one block, one partial quotient, n, and one block, a partial quotient, which is a number, I don't know, 7, by a sequence of ones.
Okay, That's clear.
So,
thank you.
Thank you. I do think that's all we have time for today, as I do need to leave now. But there didn't seem to be any more questions anyway. Mohammed, would you like me to share your email with the mailing list? So if anybody has further questions they could ask you, or would you prefer I don't?
Yes, please.
So if you have any further questions that you think of, or if someone's watching on the recording, I will share Mohammed's email. Other than that, thank you for coming, and I will see you next week because we do have another speaker. I thought this was the last talk seminar, but there is another speaker next week. I will send the information out via an email to mailing list. So thank you, and I will end the recording now.